Okay, so what this and the next chapter is about is currents, currents producing magnetic fields. So we saw these are Maxwell's equations. What these tell you is these are the causes and these are the effects. Okay, so charges produce electric fields and moving charges produce magnetic fields. So that's what the equation says. And the form of the equation, for instance, and we'll study this in the next chapter actually. The form of this equation tells you, for instance, if you have an infinitely long straight current, the magnetic fields would be concentric circles around this current, okay? And the further out you are, the weaker it'll be, and magnetic field at any given location is tangent to the circle. Okay, so these guys produce these effects, okay? And what this equation tells you is, if you have so we saw this in the last chapter, if you have an electric field, the way to detect an electric field is use a charged particle. So if a charged particle feels a force, then there is an electric field at that location. And if you want to detect a magnetic field, at any location, what you need is a moving charged particle at that location. Okay. So in this chapter we'll study this part of the equation. Okay. So you can see that there's a beautiful symmetry. Moving charged particles produce magnetic fields, and to detect magnetic fields you need moving charged particles. Okay, whatever produces is what you need to detect it. And then we saw various, okay, so magnets produce magnetic fields around them. So there must be some kind of moving charge in these magnetic materials that produce the magnetic field. Okay. And so this is the main equation we'll study. To detect this magnetic field, you need a moving charge at that location. Okay. And the force is a cross product of the velocity times the magnetic field. Okay. And the only time this charge doesn't feel a force is when the velocity is either parallel to the magnetic field or anti-parallel to the magnetic field. Okay? That's the only time a moving charge doesn't feel a force in the magnetic field. Also, if the force is zero, if the particle is at rest. So if it's at rest, it doesn't feel a force. So the right-hand rule says, okay, so again, when you take the cross product, if you turn a screw from here to there, the screw would move in that direction, and that's the direction of the force. Okay? You can also use the right-hand rule, turn from the first vector to the second vector, and that gives you the direction of the force. Okay. Now, let's say you push a car in this direction. What will happen to the speed of the car? Let's say a car is going in this direction and you're pushing it in that direction. What will happen to the speed? The speed is going to increase. Okay. Now, if you push it in the direction of the motion, then its speed will increase. But what if you push it perpendicular to the direction it's moving? Then all that happens is its direction changes. Its speed doesn't increase. Okay. So the magnetic force exerted on a negative particle is okay. Since the magnetic force is perpendicular to the direction of motion, see, the magnetic force is perpendicular to the direction of motion, it can do no work on the particle and hence cannot change its energy. So magnetic forces cannot change the energy of the particle. All they can do is deflect a particle. Okay. So if you want to speed up a particle, charged particle, you have to use an electric field. All right. So again, here's the magnetic force. So we can use this equation to define the units for magnetic fields. So magnetic fields have units of Newton. So we've seen all of this. Magnetic fields have units of force, charge, times velocity. So Newton, Coulomb, meters per second. And coulombs per second is an ampere. So magnetic fields in SI units are Newton per ampere meter. And this combination is called a Tesla. Okay. Now, a Tesla is a very large field. Planetary fields are about 10,000th of a Tesla. And so the field on the Earth, the magnetic field in this room is about half a Gauss, okay, which is, so we define, to measure planetary fields, we define this unit, Gauss, which is 1/10,000th of a Tesla. Okay. Here are some fields. So the strongest fields that we have created is about 60 to 70 Tesla. If you go to a UF lab, they do 15 Teslas in one of their microkelvin labs. Nowadays, so if you get an expensive MRI, the MRI has a 3 Tesla magnetic field. Some of the research MRIs use 7 Tesla magnetic fields. In this room, see, that's a Gauss. The magnetic field is half a Gauss. Okay. If you buy a strong magnet, it's about 100 times stronger than the field here in this room. Okay. When your brain, when the neurons in your brain fire, currents produce magnetic fields, and those magnetic fields are about 10 to the minus 13 Teslas. Okay. And that can be detected, those fields can be detected non-invasively. Okay. All right, so here's a map of the Earth's magnetic field on the surface. You can see it's not uniform, so that's a point. This is in Gauss, and it's strongest near the poles. Okay. So the Earth's magnetic field at the surface varies between 0.25 and 0.65 Gauss. Now, in this chapter, you'll do a lot of problems that are in 3 dimensions. So we will need to indicate the direction of the magnetic field. And here's the convention. So think of an arrow. Okay. Denoting the magnetic field. Magnetic fields are vectors. And if this arrow is coming out of the page, then what you're seeing is the arrowhead, the tip. And so magnetic fields coming out of the page are indicated like so. Magnetic fields going into the page are indicated by crosses. Okay. And of course, if the magnetic field is in the page, that's not hard to represent. Okay. So that's the convention. Okay. How do you detect a magnetic field? With a, yeah. So a moving charge feels a force in the presence of a magnetic field. Okay. So now, what if you have a magnetic field and you pass a current through a wire? What is a current? It's a bunch of moving charges. And every moving charge will feel a force. So the wire will feel a force. And what will be the force on the wire? It'll be the sum of the forces on every charge. Okay. So here is a force on a single moving charge. And what this tells you is that's the number of free charges, and that's the volume of the wire in the magnetic field. So that's the number of free charges. That's the number of moving charges. And that's the force on each charge. So when you have a current carrying conductor, it will feel a force like that. All right, so let's say the current, let's make sure we understand the direction of the, so if the current is moving in this direction, so you can think of it as positive charges moving like that, and the magnetic field is into the sheet of the paper, so when you turn the velocity vector into the magnetic field, the force will be in this direction. Okay. So when the current is in that direction and the magnetic field is into the sheet of the paper, the force on the conductor will be in that direction. Okay. Notice only the charges that are in the presence of the magnetic field will feel a force. Once the charges are out of the field, they don't feel a force anymore. Okay. Now, so we use the drift velocity. What we'll do is we'll associate a length vector, and the length vector is pointing in the direction of the current. Okay. So we can write a simplified expression for the force on the current carrying conductor. I is the current, L is the length of the conductor in the magnetic field, and B is the magnetic field strength. Okay. Okay. Does charge feel a force when it's not moving? No. So you see, and that if the current is zero, the conductor won't feel a force. Okay? And so here is the force on a conductor due to a bunch of moving charges. So now we'll learn something very interesting. Do you guys know who does most of the work? What does most of the work in the world? Who does most of the work in the world? 90% of the work is done by electric motors. Okay? And we'll see how they work in a second. All right? All right, so you just saw the force on a current carrying conductor. Okay. So this is the seed to show you how to convert electrical energy to mechanical energy. Okay. All right, so let's say here you have a wire like this. You just saw how to calculate the force on a current carrying conductor. So let's look at this element of the conductor. And the force on that element of the conductor is I ds. ds is a vector pointing in the direction of the current. And B is the magnetic field. Now, if you wanted to calculate the force on this entire conductor, what do? You just add up all these forces. And adding up a bunch of forces is just doing an integral. So the total force is just doing that integral. Now, of course, in general, that integral is hard to do, but let's consider the case when the magnetic field is constant. When the magnetic field is constant, this comes out, and then it's just a matter of adding these little vectors, adding all those little vectors. What is the sum of all those vectors? It's a vector pointing from the starting point to the end point. Okay? So the sum of all those vectors is just L prime, which is that vector. What is the force on a closed loop? What would be the force on a closed loop? L prime, what would L prime be for a closed loop? It would be 0. So the net force on a closed loop is 0. Okay? So the net force on a closed loop is 0. However, it turns out that the torque is not 0. Okay, so if in a uniform magnetic field you place a closed loop of wire carrying a current, here's what happens. Okay, so let's figure this out for this wire. Okay, so here's the here's the magnetic field. Here's I. L cross. So L cross. If you turn a screw from here to there, the force on this will be out of the sheet. So the force on this will be out of the sheet. For this guy, the current is like that. L cross B, the force will be into the sheet. And these guys are parallel and anti-parallel to the magnetic field, and they won't feel any force. It turns out these two forces are equal and opposite, and that's why the net force on this loop is 0. Except that what will these forces do? They will turn this loop about that axis. Okay? So there will be a torque acting on this loop, current carrying loop, in the presence of this magnetic field. Okay? And what that torque will do is make the loop turn. Okay, so the loop will turn about this axis. It'll turn like that. And here's how you remember it. Okay, so what this torque is trying to do is, so you use your right hand, stick your fingers out in the direction of the current, and your thumb is being turned toward the magnetic field. Okay, so that's what's being done. Okay, and in a second we'll learn a current. So again, stick your fingers out in the direction of the current using your right hand, and your thumb is being turned in the direction of the magnetic field. Okay, when the loop is in the plane of the magnetic field, that's when the torque is maximum, and the maximum torque, it turns out, is I the current, times the area of the loop, times the strength of the magnetic field. So the maximum torque is IAB. Okay. All right, so here is another configuration. So here is the loop. Again, what we'll do is we'll so it turns out a useful way of looking at this is a current carrying loop acts like a magnet. Okay, and we'll associate a magnetic moment with it. And we'll come to that in a second, but that's a useful way to think of it. Okay, so the torque is I times area vector cross B. Area vector is, again, point your fingers, use your right hand, point your fingers in the direction of the current, your thumb points in the direction of the area vector. Okay, and what is the torque trying to do? It's trying to line up the area vector to the magnetic field. Okay. So the torque on the loop is such that it's turning this, aligning this area vector to the magnetic field. Okay. This quantity here, I times area, is called the magnetic moment of the loop. So the torque on the current carrying loop rotates vector A towards the magnetic field. All right, so we'll define this thing called the magnetic moment. The magnetic moment of a current loop with n turns is defined as that. Okay, so the magnetic moment of a current carrying loop is I, the current, times n is the number of turns there are. and A is the area of the loop. Okay, so a current carrying loop behaves like a magnet, and the magnetic moment is the strength of the magnet. So this is called an electromagnet. Okay. And it's a very useful thing. Why is this useful? Why would this be better than, let's say, a permanent magnet? Huh? You can turn it on and off. Okay. You can change its strength, and and so on. So this is a very useful device. Okay. So the torque on this electromagnet is the magnetic moment, which is the strength of the magnet, cross B. So, again, the torque is maximum when the magnetic moment is perpendicular to the magnetic field. So in this diagram, here's the current coming out, and here's the current going in. So there's the magnetic moment, and the torque is maximum in this configuration. In this configuration, the torque is 0. Okay. All right, so let's say the magnetic field is pointing in this direction, and here's the magnetic moment. The torque acting on the moment will turn it in that direction. Now this is like, if you have this object has gravitational potential energy, and if you let go, that potential energy gets turned into kinetic energy. Just like that, when this guy gets turned in, the potential energy gets turned into kinetic energy. So we associate a potential energy with a magnetic moment in a magnetic field, and the potential energy is defined as negative of mu dot B. So right now the potential energy is 0 because mu and B, if the magnetic field is in this direction, and when mu is pointing in that direction, that's when the potential energy will be maximum. Okay. So the torques would turn this all the way till there. Okay, these devices are very useful. These things are very useful. So for instance, you can use these devices to turn satellites. So let's say you have a satellite up there in space, and for some reason it gets misaligned. You can turn it back using torquers. Okay, so for instance, here's a satellite. If you have a torquer, right now its angular momentum is 0. If you turn a torquer like this, the satellite will turn in the opposite direction. And so what you do is, these satellites have these torquers, which are just loops of wire, and you hit a button on your computer, pass a current through these loops, and they're using the Earth's magnetic field. The loop will move and turn in the direction of the magnetic field, and the satellite will move in the opposite direction. Okay, so you can turn a satellite by passing a current, and once you have turned the satellite enough, you just shut the current off and the satellite will stop. Okay, so these torquers can be used in low Earth orbits. If you're too far above, for instance, these are not useful for geostationary satellites. Okay, so you have to be close to the surface of the Earth, so they can be used in low Earth orbits. And the advantage they have is, then you don't have to have thruster fuel. You don't have to So if a satellite is going to be up there 10, 15 years or whatever, you don't have to plan for thrust or fuel for 10, 15 years. You can use electricity from solar panels. Okay. All right, so here is a magnetic field into the sheet of the paper. Okay. Let's say we throw a positive charge in this direction. Okay. A moving charge in the presence of a magnetic field will feel a force. So the force on this will be V cross B. The formula is Q times V cross B. And V cross B, B is into the plane, so V cross B would be a vector in this direction. When it's here, V cross B would be a force in that direction. So you see, if you throw a positive charged particle like that, it feels a force perpendicular to its motion, and what it'll do is it'll go in a circular orbit. So this force, the magnetic force, is really a centripetal force, and so that's equal to mv squared by r. Okay. And so this is the angular frequency. So a charged particle, when you throw it perpendicular to the magnetic field, it'll go in a circular orbit. And you see, the magnetic field lines have trapped this particle. Okay? And the particle is going in a circle. And the angular frequency, the number of times it goes around in a circle per second times 2 pi. 2 pi times the frequency is given by V by R. And that's proportional to the magnetic field. The stronger the magnetic field, the more times it'll go around in a circle, and is inversely proportional to the mass. Okay. But the important thing is you can trap charged particles using magnetic fields. Okay. Now let's look at an interesting application. When does a moving charged particle not feel a force in a magnetic field? Yeah, that's right. When the velocity is either parallel or anti-parallel to the magnetic field. Okay. If the velocity is perpendicular to the magnetic field, then that component makes it go in a circle. So now let's do the following. In a magnetic field, let's give the particle a velocity component parallel to the magnetic field and a velocity component perpendicular to the magnetic field. The perpendicular component will make it go in a circle around the magnetic field, and the parallel component is unaffected. So if you throw the particle at an angle, what it ends up doing is it just spirals around the magnetic field line. So a particle thrown at an angle to the magnetic field spirals around the magnetic field line. All right, well, why do we care about this? So you can make devices like these. Okay. So here are charged particles that can spiral around magnetic fields like that. And it turns out that if the field gets stronger, there's a reflecting force. Okay? So this particle goes around the field, and when the field gets stronger, it's reflected backwards. And then when it hits a stronger field here, it's reflected backward here. So you see, you can have these charged particles that are trapped in this device. And why do we care about this? You can take hydrogen nuclei protons, heat them up to billions of degrees of Kelvin, and trap them in these magnetic bottles. They will never hit the wall and vaporize your balls. So you can use them in fusion reactors. So this is called a magnetic bottle. Now, this configuration is not used very much. A donut-shaped Tevatron is used much more, but we'll come to that in a second. Anyway, so you can use these devices and have protons at billions of degrees and not have them hit walls and stuff like that. Okay. Now here's another application. Okay, so the sun is shooting out electrons and protons. So the sun has the sun's surface temperature is hot enough where there's enough ionized hydrogen, and these guys can escape the sun's gravity. The ones with high enough energy can, and this is the solar wind. Okay. We just saw that the Earth's magnetic field is like that, and as these guys come in, they get trapped in the Earth's magnetic field. And if they have a velocity tangent to that, they'll go spiral around in the magnetic field lines and go around over like that. When the field gets stronger, they reflect, and then they'll bounce back. Field gets stronger, they'll reflect back. Okay, so these solar wind particles get trapped in the Earth's magnetic field, and they oscillate back and forth. Okay, so and they'll go back from pole to pole in a fraction, in a matter of seconds. These particles trapped by the Earth's magnetic field spiral around the field lines from pole to pole, covering the distance in just a few seconds. Okay, and this is to scale, sort of. So you have these are called Van Allen belts, and so here's the Earth, and imagine a donut shape. So the Earth is surrounded by shells of these charged particles. And in these shells, these charged particles are going back and forth. Okay. So these shells of particles, the Van Allen belts extend between 1,000 kilometers to 45,000 kilometers. The radius of the Earth is 6,400 kilometers. Okay. So the lowest belt is about 1,000 kilometers, and then 7 times the size of the Earth. Okay. Now here's the deal. When these particles get close enough, so if they get within 50 miles of the Earth's surface, they start hitting enough atmospheric atoms, they excite them, and those are the aurora borealis. Those are the auroras. When these particles hit and excite the atmospheric molecules, when those molecules de-excite, they emit light. Okay. So when these particles are near the poles, they collide with atoms in the atmosphere, causing them to emit visible light. Okay. So the auroras. Okay. So auroras result from emission of photons in the Earth's upper atmosphere, about 50 miles, from ionized nitrogen atoms regaining an electron, and oxygen and nitrogen atoms returning from an excited state. So these particles, when they bump into the atmospheric molecules, they excite them or ionize them, and those particles, those excited atmospheric molecules, emit these light. So oxygen emissions are green or brownish red. Nitrogen emissions are blue or red. Okay, so blue or red. In the northern hemisphere, the night lights are called aurora borealis. In the southern hemisphere, they are called australis, aurora australis. Look at this. So Jupiter has auroras. Here's the Earth's auroras taken from the space station. Here's Saturn's auroras. What does it mean when you have an aurora? When a planet has an aurora? That means it has a magnetic field. That means it has a liquid metal core producing the magnetic field. Okay? So that's why we look at that. Okay? A planetary aurora indicates the presence of a magnetic field on the planet and thereby implying a liquid metallic core. Okay. Okay. What is the mass of the hydrogen atom? What's the mass? 1 atomic unit, which is about 1.67 times 10 to the minus 27 kgs. How did they get that mass? So here's how they weigh it. So here's how they weigh all these atoms. All right, so here's a source. Let's say you want to weigh some gas. You can ionize it, and then so through an oven, ionize it and spit out these hot gases. It goes through a slit, and here's a charged particle traveling at a velocity v. You have an electric field in this direction and a magnetic field in that direction. So perpendicular electric and magnetic fields. So the magnetic field is into the sheet, here's the electric field, and here's a charged particle, and let's say it's a positive particle. The magnetic force is in that direction, and the electric force is in this direction. Now, if the particle is going too fast, this force is greater, and the particle would hit that plate. If the particle is going too slow, this force is great, and it'll hit this plate. Only particles with the correct velocity will go straight through. So this is a velocity selector. So what you can do is you can ionize particles and shoot it through here, and particles of this velocity will get through straight. So this is a velocity selector. Okay. Now if you want to weigh any of one of those guys, all you do is ionize it singly, and then pass it through this, and now you know a single ion and singly charged ion that's going at a specific velocity. And then what you do is pass it through a region where you know this magnetic field, and this magnetic field will make it go in a semicircle. The heavier the mass, the heavier the particle, the bigger the circle. And so to get the mass of the particle, you just measure the radius of the particle. And so that's how they weigh all of those guys. Okay. So the mass of the particle and divided by its charge is the radius of the path times B naught, that's the field here, and E by B is from the velocity selection. Okay, so if you want to weigh an atom, this is what's called a mass spectrometer. Okay. That's how they weigh all these atoms. Okay. Our chemistry labs have a mass spectrometer. I don't know if you guys have used them. I'll briefly mention the Hall effect. So here's the Hall effect. Okay, so let's say here's a piece of wire, a flat piece of wire. You pass a current through it in the presence of a magnetic field, perpendicular magnetic field. If you pass a current through this in the presence of a magnetic field, if the charge carriers are negative, what will happen is in the presence of a magnetic field, some of them get deflected. A bunch of negative charges will collect here and positive charges there. Okay. In steady state. So when you pass a current in the presence of a magnetic field, a voltage perpendicular to the direction of the current develops. And here is the same current. If the charge carriers are positive, the voltage, this end electrons will collect over here, or positive charges will collect over here. And you see, depending on what the charge carrier is, the Hall voltage, this perpendicular voltage is called the Hall voltage, has a different sign. Okay, so the current is in this direction, the magnetic field is in this direction. In metals, the charge carriers are electrons, but there are semiconductors where the charge carriers are holes, and those, you can think of those as positively charged particles. So the Hall voltage would be opposite. Okay, so the Hall voltage is proportional to the current, to the magnetic field, and this width of this wire, and the carrier density. So you can measure the carrier density, you can measure the charge from the sign of the voltage, you can measure the carrier charge, and A is the area of cross section. You know. So using the Hall voltage, you can measure the carrier density. Okay. So for instance, how many free electrons there are in this metal can be measured using the Hall voltage. Okay. All right. Do you guys want to hear about the MRI machine? Okay. I'll come back to that in a second. Let me tell you how a speaker works. Let's first do this thing. So, what is an electric motor? What is an electric motor?
Convert electrical energy into mechanical energy.
That's right. So, an electric motor converts electrical energy to mechanical energy. And you just learned the secret of how it does. So in an electric motor, you have permanent magnets that are producing this magnetic field. And if you pass a current through a wire loop, this wire loop acts like a magnet. Remember, have your fingers point in the direction of the current, and your thumb, so there is the moment, and the magnetic field is turning the moment in the direction of is trying to line up the magnetic moment along. So here's the loop. Here's the magnetic moment. And what is the torque doing? It's lining this guy up in that direction. And once this thing lines up like that, once it's lined up like that, then what do? So it's lined up like this. You switch the direction of the current once it lines up like that. Now the moment is pointing like that, and the torque is again going to try and turn it like that. When it lines up, you switch the current again. That's how the electric motor works. Okay, so you have so in the electric motor, here's the magnetic field pointing in that direction. Here's this loop of wire. Here's the loop of wire carrying a current like that. As soon as it lines up like this, now you flip the current. You keep doing that. Okay. So that's how the electric motor converts electrical energy to mechanical energy. Okay, so the torque on a current carrying loop uh, converts the electrical energy to mechanical energy. Okay. So this configuration is a DC motor, and then you can, depending on how the wires are connected to the outer wall, you can have an AC motor as well. All right, let's now talk about how a speaker works. Okay, how do you produce sound? How do you produce sound?
Making vibrations in the air.
What's that?
Making vibrations in the air.
Yep. So if you have any sort of a diaphragm, if you can make it oscillate, you can make it vibrate, then you can produce sound. So you can take this sheet of paper and make it oscillate, and you can produce sound. Now you just have to figure out how to make it oscillate. Okay, so here's the diaphragm. Okay, we got to make it oscillate. All right, so what is a loop of wire carrying a current? It's like a magnet. Okay, so and the way this behaves like a magnet. Point your fingers in the direction of the loop. Your thumb points in the direction of the magnet. So this loop carrying a current is behaving like a magnet with the north pole like that and the south pole like that. Okay. Now what you do is, here's a diaphragm. To the diaphragm you attach a magnet. So here's this piece of wire, and you pass the current through this. And here's another magnet which is attached to this diaphragm. Okay, when you pass a current in this loop in this direction, this is a south pole. What does it do to this south pole? It repels it. It'll push this diaphragm in this direction. When you switch the direction of the current, pass a current like that in this wire, this becomes a north pole. It'll attract the diaphragm. So by switching the current back and forth, you can make this diaphragm vibrate back and forth. So you'll convert this electrical signal into mechanical vibrations. And that's how a speaker works. Yep. All right, so I'll briefly go over this MRI machine, which is a pretty good technology. Yeah. So in the MRI machines, so in this cavity, the fields are 2 to 3 Teslas. Okay. And so the patient is inserted in there, and 3 Tesla is a very strong field. Look at this gurney so the gurney was in the room and somebody turned on the machine and this gurney went flying in there. Okay. So that's a very strong field. They use superconducting wires, so these are superconducting magnets. Okay. Use superconducting magnets. Okay. Now here's the basic technology. So your body has a lot of water molecules. Water molecules is H2O. Okay. So there's a lot of hydrogen atoms in your body. And the proton has a spin half. That's what they use in the MRI machine. They're using the proton in the which is the hydrogen nucleus. Okay, so if you have a magnetic field like this, and the magnetic moment, remember the energy is, the potential energy is minus mu dot E. Okay. All right, so when the magnetic moment is lined up with the magnetic field, then this is a low energy configuration. When the moment is anti-parallel to the magnetic field, this is a high energy configuration. Okay. So, where's my rough book? Okay. So now we'll, so here is the technology. So this is the low energy configuration, this is the high energy configuration. And the energy difference, so this is low energy configuration is magnetic moment is parallel to the magnetic field, and high energy configuration is magnetic moment is anti-parallel to the magnetic field. The energy difference is proportional to the magnetic field strength, among other things. Okay. Now, so under normal circumstances, so there are more protons in the low energy configuration and fewer protons in that high energy configuration. Okay. Then what you can do is you can send a pulse, electromagnetic pulse of the right energy, and then excite these guys over there. Okay. And then when they de-excite, when they go back to their normal state, you take a picture of these photons. Okay. So that's what you do to get an image. Okay. All right. Again, so these protons that are in parallel with the magnetic field, those are low energy photons. Okay. So that's a higher population, and this is a lower population. You excite them by sending a photon of the energy exactly equal to that. Some of them will get excited, and then when they de-excite, they'll emit these photons, and you take pictures of these guys. Remember, this energy difference is proportional to the magnetic field. Okay, so that'll be crucial. Okay, so now let's go back to there. So MRIs use magnetic moments of protons, hydrogen nuclei, for imaging. Magnetic moments have a tendency to line up with the direction of the magnetic field. Energy difference of the two spin levels depends on the field strength. So energy difference depends on the field strength. So here's the crucial part now. Okay. So in an MRI machine, you can take picture of that point inside your brain. How do you take a picture of something inside your brain? So here's what they do. So inside there, the field is, let's say, 3 Tesla, but then they have gradient magnets which make sure that the field is different at every location in that grid. That's what this thing is. So these are gradient magnets that are making sure that at every point the magnetic field is different. So if the magnetic field is different at every point, the energy difference will depend on the value of the field, and you can excite those particular hydrogen nuclei, and they will emit light. They will emit the light. So you use the excitation frequency that corresponds to that magnetic field, and you take a picture of that. And then when you want to take a picture of the next point, you change the magnetic field to correspond to that point. And so you can take a picture of that point. So you take pictures point-wise. Gradient magnets are turned on and off very rapidly in a specific manner, altering the main magnetic field at a very local level. This allows one to pick exactly which point to take a picture of. Okay. And then you keep changing the points, take pictures one point at a time, and then assemble a three-dimensional picture. Okay. So it's a very good technology. Okay. Pulses cause protons in the area to absorb energy and jump to a higher level. This is the resonance part of MRI. MRI stands for magnetic resonance imaging. Okay. When the RF pulse is turned off, photons begin to, okay. So here's the magnetic field. This is the high energy configuration. This is the low energy configuration. When you excite it to that, and then when they de-excite back, they'll emit the photons. When RF pulse is turned off, protons begin to return to their natural alignment by emitting RF photons. The coil now picks up those photons and the information is transformed into an image. Yeah. All right, guys, we'll stop here.